The last lecture was the last on wave optics or physical optics as it is sometimes called, and the last topic in the wave optics was the polarization. And I told you, in fact emphasized, that only transverse waves can be polarized. The longitudinal waves cannot be polarized, because there the particle vibration is along the direction of propagation. And then we learned how polarized light can be produced by reflection, by refraction, or by scattering. There are several ways. This example is the reflection at a certain angle called Brewster's angle. Here the transmitted ray and the reflected ray, they are perpendicular to each other, and therefore, this is plane polarized light, because it cannot carry this direction of vibration. It is along the direction of propagation of light, and it is prohibited. Therefore, this light, reflected light, is plane polarized. And if there are two plane polarized lights, if their amplitudes are equal and their phases are equal, then we get the net or the resultant vibration inclined to both. And if there is a phase difference and the amplitudes are equal, then we have circularly polarized light, that is, the plane of polarization rotates along that circle. And if the two amplitudes are unequal, but phase difference is 90 degrees, then we have elliptically polarized light, that is, the plane of vibration now moves in all directions and traces out an ellipse. Now, from this lecture on, we shall for the next several lectures be considering dual nature of matter. Let me summarize what we are going to do. Dual nature means that the waves like light, for example, can behave like particles, and particles like electrons or neutrons can behave like waves at times in certain situations. This is dual nature of matter. Now, this dual nature of matter can be understood or appreciated only if we know the nature of matter itself. So, we shall spend the 1 or 2 lectures to review the history of the understanding of the nature of matter, how we understood the nature of matter. Remember that many great scientists participated in this. There were discussions, experimentations, and whatever, and they arrived at what we now know today, the nature of matter. So, we must know the nature of matter today before we appreciate the dual nature. So, let us consider the atomic theory of matter. You are familiar with the fact that in a chemical reaction or a chemical change, new substances are produced. I will take this reaction as an example. NaCl plus AgNO3, sodium chloride plus silver nitrate would give you sodium nitrate plus silver chloride. And these kinds of reactions in which new substances are produced, these chemical reactions, there are 3 laws which govern these reactions. These 3 laws are the law of conservation of mass, the law of definite proportions or law of definite composition, and law of multiple proportions. These 3 laws we shall study, which govern the chemical reactions, and from this we shall extract the nature of matter. Law of conservation of mass was discovered by Lavoisier. If you remember, I think he was also the person who discovered oxygen. The law says that in a chemical reaction, the mass of reactants is equal to the mass of the products. Let us take this reaction. What he said was that the mass on this side of the reaction equation is the same as mass on the other side of the reaction equation. In truth, however, there may be very small changes in mass in a reaction, but these changes may not be easily detected. And Lavoisier, who was working maybe 200 years back, did not have very sensitive instruments. So, as far as he was concerned, there was conservation. The mass on both sides of the chemical equation was equal. We can say, in modern perspective, we can say that in a chemical reaction there is no detectable difference in mass on both sides. the mass difference is very small, it is not easily detectable, but there is mass difference. All right, let us take the next one, law of definite proportions. This was discovered by Proust. Here he says that if there are two elements which form a compound, then these two elements to form that compound would always enter in the same ratio, whatever the source of that compound. For example, you take water. Let me state the law clearly again. A given chemical compound, the elements forming the compound combine always in the same proportion by mass, whatever the source and size of the sample of the compound. For example, hydrogen and oxygen, they form water, and they enter in the ratio of 1/9 to 8/9 by mass. The proportion of hydrogen is 1/9, proportion of oxygen is 8/9, and this proportion would be the same whatever the source of water and whatever the size of the sample. For example, the water contained in this bottle, or water coming out of the tap, or water contained in the rivers and oceans, wherever you take this water, hydrogen and oxygen mix in the ratio 1/9 to 8/9. That is law of definite proportions. This was discovered by Proust. Here also there are exceptions, but again at the time Proust was working, you could not really find out these small changes. Then let us come to the law of multiple proportions. This was discovered by Dalton. John Dalton was an English scientist and very famous for many other things, and he is said to be the father of atomic theory. So, Dalton discovered this law of multiple proportions. What he says is this: if you have two elements x and y which form a compound, then for a fixed amount of x, the amount of y that would be required to form different compounds would be in simple ratios, would be simple multiples of one another. Let us repeat. You see, x and y combine to form more than one compounds. For example, N and O, they form NO, they form NO2, they form N2O3 and so on. So, let us take elements x and y, they form different compounds. Now, if I fix the amount of x, then the amount of y required to form these different compounds, this would be in simple multiples of one another. Let us take the example. Here we have carbon monoxide and carbon dioxide. The proportion of carbon is 42.9 in terms of mass, proportion of oxygen is 57.1, and therefore, for a unit mass of C, the amount of oxygen is 1.33. In CO2, the proportion of carbon is 27.3, proportion of oxygen is 72.7, and for a unit mass of C, the amount of oxygen required is 2.66. You can see that 1.33 and 2.66 are in simple ratios 1 to 2. That is what Dalton said, that if there are two elements form different compounds, then for a fixed amount of one element, the other combines such that the masses required of this compound of this element are in simple ratios. Let us take another example just to make this sure that this is all right. Let us take now example N2O3 and NO, and the proportion of N is given, proportion of O is given, and you can see for a given proportion of N, the proportion of O required, or the ratio of O to N, is 1.71 and 1.14, and you can see they are in the ratio of 3 to 2. 0.57 times 3 is 1.71 and 0.572 into 2 is 1.14. So, they are in the ratio of 3 to 2, again a simple ratio, simple multiples of one another. This might break down in certain cases, again those cases are probably were not known at that time. As far as FeO and Fe2O3, ferric oxide and ferrous oxide are concerned, they are fine. But if you take ferric oxide Fe3O4, this is a ferrous oxide, ferric oxide, this is another compound Fe3O4. Here the ratio is not, this one is not in simple proportion to this and this, these two. The first ones are in the ratio of 3 to 2, but the third one you can see does not form a very simple ratio. Actually, it was discovered later that Fe3O4 is composed of FeO and Fe2O3. So, considering all these laws and the chemical equations, Dalton formulated the atomic theory. What did he say? First, all matter is made of atoms. Atoms are indivisible and they cannot be destroyed. All atoms of an element are identical in mass and other properties. All compounds are formed by the combination of atoms of two or more elements. All chemical reactions are rearrangement of atoms. We saw that example. NO3 got detached from Na and was attached to silver, right. So, all chemical reactions are rearrangement of atoms. Now, the first postulate, this atoms, was this name atoms and a similar idea was propounded long back by Greeks. So, he borrowed the term from them and called them atoms, and atoms are indivisible, they cannot be destroyed. Now, of course, we know that atoms can be divisible, I mean in protons and electrons you can separate them. In chemical reactions, however, the atom remains an indestructible quantity. In regard to the second postulate, it may be said that the modern development in science have revealed that within an element there may be atoms more than one kind. You see, what was the second? All atoms of an element are identical in mass and other properties. Now, we know that the elements consist of several kinds of atoms. They have the same properties, chemical properties, but their masses are different. These are known as isotopes, as you know. So, this was not known at that time. Now, we know there are isotopes. These are, for example, there are isotopes of carbon, carbon 12 and 13. There are other isotopes also, but these are the major ones, carbon 12, 13 and carbon 14. And carbon 12 and 13 are stable, but carbon 14 is radioactive, and this is actually the basis of radioactive radiocarbon dating. You see, if you have a very ancient fossil, then by counting the number of carbon atoms, carbon 14 atoms, you can find out how old this is, because we know the half life of radioactive carbon. So, this is the basis of radioactive dating. In regard to the fourth postulate, what is the fourth postulate? That atoms simply rearrange themselves, right. So, atoms of chlorine attach themselves to silver and give us silver chloride. Atoms forming nitrate, they get attached to sodium to give us sodium nitrate. So, there is just rearrangement of atoms in a chemical reaction. These were the four postulates of the atomic theory of Dalton. You see, the postulates of Dalton were actually the work of many scientists working over several centuries, in fact. So, it is not only the work of Dalton. Dalton drew all these conclusions on the basis of the work done earlier, and this happens in science very often. Now, the arguments that went into formulation of these postulates, they are not simple. As I said, they were developed over a very long period. However, if we accept those postulates, then we can understand the laws of chemical reactions, the laws which governed the chemical reaction, like conservation of mass, and then what were these laws? One was the conservation of matter, then it was law of definite proportions and law of multiple proportions. We can understand these laws if we accept the postulates. However, the process was reverse. These laws were first studied. On the basis of these laws, arguments were given, debates took place, and then they were distilled in the form of the postulates which Dalton formulated. It is a fascination piece of history of science. It is a very interesting history, how science evolves and how long sometimes it takes for the science to evolve. All right. Now, the Dalton theory was formulated in the early years of 19th century, and the first model of an atom was possible in the beginning of 20th century. It took almost 100 years to have models of atoms, and the first was the Thomson's model. Thomson, was studying the cathode rays, and he showed that they were actually streams of electrons, negatively charged particles, now called electrons. And he also found that the mass of each electron is roughly 1,000th time the mass of an hydrogen atom. So, he discovered all this. He was working on the cathode rays. Why are these called cathode rays? Because most of these experiments were done with vacuum tubes, and there was a cathode to which the electrons were attracted, and therefore, they were known as cathode rays. Cathode rays are actually electrons. Thomson suspected that these particles, these electrons, come from atoms, but he knew also that atoms are neutral, because matter as a whole is neutral, therefore, atoms must also be neutral. So, he thought that electrons and the positive charge must be mixed in some way, so that the atom as a whole is neutral. So, he formulated this model of atom called plum pudding, because these electrons, see, there is a sphere consisting of positive charge uniformly distributed, and in this are embedded negative charges. The total negative charge is equal to the total positive charge. So, the atom as a whole is neutral, but these appear like plum pudding. If you have seen plum pudding, then there is a pudding and you see plum at various points. It is called the plum pudding model of atom. This was formulated by Thomson. Now, what are the implications of this model? As I said, since the electrons are very light, most of the mass consists of the positive charges, right. And there is another thing, since positive charges and negative charges are distributed almost uniformly, therefore, the electric field of electrons and protons gets cancelled to a large extent, and therefore, if there is at all an electric field left behind, it would be very weak. So, this was one of the predictions of this model, that this atom would have a weak electric field. So, that if we throw a beam of alpha particles, then they would go through this, because the electric field is weak, they would not be deflected very much, and they would just go with very little deflection, they would go straight. Let me repeat, the electric field inside such an atom must therefore be quite weak. So, the prediction of the plum pudding model was that most of the alpha particles shot at a thin film of gold would be deflected by small amounts and would travel almost directly to the detecting fluorescent screen behind the foil. Let me show you this. I will show you in the next lecture, but here I am going to point out a very important thing. You see, in science, all theories, even the most famous ones, are tentative. They may be well founded, all the predictions may have been fulfilled, theory is well established, but it is still tentative. That means, this theory can be revised, either by small amount or substantially, or even discarded if new facts emerge which go against this theory. The theories can be revised, improved upon, or abandoned altogether if new evidence emerges to warrant such changes. You remember, in the ancient times we had this theory known as geocentric universe. At that time, it satisfied all the observational facts. However, this was replaced, I think for about 1800 years or 2000 years, this was accepted. But when new facts discovered by Copernicus and Kepler and so on, new facts came, then the older theory was rejected and a newer theory, the heliocentric theory, was formulated. Even that was replaced later on, but the point is that all theories in science, see, that is the excitement of working in science, that you know that every theory, I mean, now we people swear by theory of relativity, but I am sure there are large number of scientists, researchers working on to find maybe more improved theories of relativity, or even theories which would replace theory of relativity. Newton's theory, which was for 200 years, it held sway, everybody accepted it. Not only in science, even philosophers accepted this theory and formulated their philosophies around the Newton's theory of mechanics. However, after 200 years, the theory was improved upon by Einstein. He gave the theory of relativity, which contains Newton's theory as a part of it. For several observations, we invoke theory of relativity to understand those observations, because Newton theory cannot satisfy those observations. So, the point is that the older theory has been replaced by a newer theory, although the theory was well established. So, in science, nothing is final. We accept the theory, any theory, as it is today. It may not remain there tomorrow, or a year after that, or maybe in 100 years it might be replaced by a different theory, but the theory must be replaced. In fact, one of the philosophers of science, Karl Popper, says that a theory is regarded good if it predicts phenomena that, at least in principle, can falsify the theory itself or prove it wrong. That means, if you formulate a theory, you must also predict what phenomena can be predicted from this theory, and if those phenomena are not actually observed, then the theory will be thrown out. And a good theory is one which predicts phenomena which can falsify the theory in principle. So, this is a very important principle of science. In science, we cannot say this is definite, this is fact, this is finished. No, the things never finish. The research continues, and newer theories are found. In the next lecture, I will continue with the models of atoms. We shall see Rutherford model, we shall also see its shortcomings, then we will come to Bohr model and Bohr postulates, then emission and absorption of radiation by atoms, and ultimately ionization potential of an atom. That is in the next lecture.